I think it's 1:20. Let me just start the clock here in mind as well. Good afternoon, everyone. Thank you for coming to Scala Days and B, more specifically, coming to this talk about advanced JVM production debugging. I hope everyone can see me and the presentation well. A few words about myself. Tal, co-founder at Takipi, where we focus primarily on production debugging of high-scale systems in Java and Akka. I've been coding and designing systems, I would say, for the past 15 years, primarily in C++ and in Java, veering in the last year much more towards Scala, where we see a lot of traction. A lot of my focus has been on real-time systems and systems that scale. I blog in a bunch of places, but primarily over at blog.takipi.com about a bunch of stuff within this domain. So hopefully some of it will be relevant to you guys in the future. And I have kind of good news and bad news. So I was asked into sub for another person like 2 days ago. So that was the bad news or the good news, depending how you look at it. Probably bad news for you guys, good news for me. But the other way around is that this actually enabled me to, it means that today I'm going to go a bit deeper with you guys. A lot of time I have like a cookie cutter demonstration where I've kind of prepared in advance. This actually, because of the lack of time, I'm going to go deeper and show you some stuff that usually I don't find the time or opportunity to dive into when I'm giving these talks. So hopefully everything will go well and you guys will find it useful. With that, let's get to it. First of all, just kind of setting, when I say production debugging, just want to set the terminologies. What do I mean? Which is, the process by which we isolate state and distributed systems, which is causing abnormal behavior. Okay, so this is what we're going to be focusing on. How do we isolate the state of an application within a running system in production to enable us to get to the root cause of whatever it is we're trying to fix? The biggest difference when you say debugging, production debugging, is that normal standard debugging we do every day in our IDEs and stuff is usually forward tracing. Meaning we have an error or something, we start up the debugger and we move forward in time. We let the application kind of take us there. The big difference between that and production debugging, as I've seen with many customers that production debugging is by definition backward tracing. Meaning something happened and it is up to you to obtain the forensic evidence that will enable you to go back in time and understand, all right, this is the root cause of the problem. And this is what it boils down to, evidence. We want to make sure that in production debugging, the better evidence that we have, the better state that we've collected in advance will essentially lead us to a solution much, much faster. And that is essentially what I want to talk about today. Some standard techniques going from some things which are foundational, I think most people should have, especially when we're dealing in reactive applications and systems that run at scale. And from there on out, we're going to touch on some techniques which are a bit more advanced and out there, and I think are both interesting and, in my experience, have helped many of our customers in the past. I'm going to talk a bit about foundational logging, especially when it comes to distributed systems. We're going to move on to how can we really kind of hyperdrive our thread dumps and our JStacks, and when we analyze thread activity within our JVM. We're going to talk a bit about how can we do dynamic state extraction, one of the most powerful tools and kind of unsung JDK heroes, which is btrace, which I love, and I think most developers who are dealing with production environments should have a good handle on. And the last thing, I'm going to go a bit deeper and talk a bit about Java agents, JVM instrumentation, some of the amazing capabilities of stuff that you can do there. And if we have time, touch a bit on how those actually flow in very interesting ways into Akka as well. Lots to talk about. So first of all, let's talk a bit about logging. Logging is probably one of the biggest pieces of coding, I would say, of running production systems that has gone through dramatic changes over the past few years. We've gone through logs, which are essentially these text files which are meant for us, to log files, which are essentially now most of all consumed by machines. But that means we also need to change the way by which we approach them when we code. And this, to me, really signifies the move from content to context. Meaning, nowadays, when we log, a lot of the information we feed is not something that we're finding ourselves gripping into or opening up in a text editor down the road. It's going to feed into Logstash or to our ELK and essentially be visualized. And that, for the most part, is context, which to me is a lot of focus about thread identification, transaction identification, and some of the bits of pieces of information that are mandatory. And unfortunately, I don't see enough in a lot of production systems today. When I mean transaction identification, I mean that nowadays, as I said, most of the work that we do is for distributed, especially if you're working with Akka or Reactive code. A transaction will no longer flow on a single thread. Okay, you will not block. You will not have an inbound request, go to a database block. So the thing is, it's going to flow between all these different actors. And today, still, at the JVM level or the foundational level, there's no support to give us like a StackTrace for a message that's been passing through a bunch of actors and kind of explodes or encounters a corrupt situation, kind of state at the end. We have to then backtrace. And the way to do that is through really, really good transaction IDs. This is kind of the level of logging that we want to have nowadays. And essentially, it means that every logging component should have both timestamps, identification of customer-specific information. For us, this is actually taken from our logs. You know, the S427, which you see there, the S4247, that's actually something that identifies a customer ID. Then within that, okay, we have some specific information. Here's the cursor. Okay, we have some specific information for the actual job that's failing. But the thing that's most important is this. And hopefully you guys can see my cursor, beautiful. Transaction ID. This means that you need to assign to any message that enters your system nowadays an ID which will follow it. Because until the point that JVM is able to provide you with a distributed call stack, this is going to be your call stack. This is going to be your only means to be able to come in and through your Logstash be able to backtrack and identify exactly the course by which this message flowed through the system. Okay? So that's one thing which I want you guys to think about, which, do we have enough context? A lot of the times it's less about putting a huge string full of variables in the code, but making sure that you'll be able to backtrack and backtrace this specific bit of information. Some pitfalls that I've seen, essentially with logging, especially around performance. Nowadays, the biggest, challenge I see within companies that they can no longer process the amount of log data which they're logging to file. It's very easy for you to add a log statement into your code, but then to make sure that bit of information can actually be reduced by your Logstash or by your Splunk without incurring material costs is big. So we have to make sure that in terms of performance, we're not just not impacting the local JVM with increased I/O, but also we're not swamping our log reduction cluster. And the three biggest pitfalls that we see that impair that is what we call hot logging. Essentially, even this little snippet of code here, which seems to be fairly trivial, okay, I just process data in a stream. Okay, this can be running, anywhere within my cluster. It can be something I'm reading from a Reactive stream, or I'm reading it off my Splunk cluster, or just from any standard data set. Okay, throw an exception. Okay, encountering exception, catching that. Okay, it doesn't matter if it gets caught here. It's going to go to another actor, and we're going to log that and continue in a hot loop. That is very dangerous. Okay. Whenever you are logging now in a streaming situation, or in a situation where you're either in an explicit loop or an implicit loop, because this is a string job, you're pulling stuff off your cluster, you have to be extremely aware, because there's chances here they're going to impact performance materially, both on the local node, but also on the target reduction cluster. Also, try not to log, especially any implicit loops, which may be result in somebody hot looping you within a toString. So try not to log polymorphic objects of which you have no control. If you're logging for yourself, throwing a hash map into the log is easy and can provide you with a lot of meaningful information a lot of time. If you're doing this within a big data reduction job and you're starting to encounter mass amounts of error, this can lead to tragic results within your logging infrastructure. Okay, so these are just some of the pitfalls and the best practices. I want to jump in directly to a next subject, which is actually more interesting. We're kind of notching up, which is thread naming in production. This is one of, I think, in terms of unsung heroes, probably one of the most important properties of the JVM, which is sadly so underutilized, especially in production debugging situations. And again, doesn't matter if you're using Java or Scala, okay? People think for some reason this is something that's immutable or that should be managed by a container. That is something that is sadly not true. And that is also something that can be dramatically helpful to you. Let me give you guys an example, okay? This is what we're used to seeing, okay? If I take a thread dump, I profile any JVM today, okay, and I'm using Akka, Spark, Play, best-in-class technologies, I'm going to see a ton of threads. For the most part, they're either waiting, okay, in our thread pool, or even they're doing anything. We're just going to see a call stack. But in terms of actual state information, it's going to be fairly empty. What we want to do is start enriching that. Meaning we want to start weave in state information directly into our thread names, because this enables us, when we take a thread dump, and I'll show you a couple examples, to actually understand what this thread is doing. Okay, which message is it processing? Which queue is it working on? What is it doing? And most importantly, especially when you're trying to tune or to profile, having a timestamp which tells you when the thread took control, when essentially your code took control over the operation, is crucial. Because if you're trying to debug and to performance tune a JVM that's kind of hanging or slow, you come in, you take a thread dump. All the threads may look the same. You may not actually know which of these is the one that's hanging, that essentially is not finishing, is doing a hot loop, or is blocking for the longest period of time, and you don't know that. By using this design pattern and coming in here, essentially taking a thread dump, you're going to see that immediately. It will also propagate into any other profiler tool which you guys use. You're going to use JStack, you're going to use Mission Control, YourKit, whatever. You'll also see that information there. So it's not just, I have to come in and print a StackTrace or attach my JVM. Any professional with that information, that is essentially your only window into injecting live state information into a thread dump. Now, especially nowadays, when we look at StackTrace, especially modern StackTraces with Scala and Java 8, they're pretty hard to read. Okay, it's because compilers, modern compilers have really, they add a lot of layers of abstraction. So just analyzing a thread dump in production to understand what is this JVM doing, or this exception in the log file, okay, without any state information, it's hard to figure out what this thing is doing, okay? This is no longer just kind of the something that's happening for Scala. Even in Java 8 with lambda expressions, same deal. Okay, so if you're moving to more kind of modern frameworks and stuff, this technique will be super helpful. I'm going to rant here for a second. If you guys are using Nashorn, okay, for Java 8, I don't know if some people are, over there running JavaScript within the JVM, over the stack traces, because it's interpreted, they don't even relate to the actual JavaScript code. So if you don't have any form of identification, thread identification, what this thread is doing, this is practically meaningless. Okay, so this is a little rant here. Let's talk a bit about JStacks and thread dumps in general. Let's take it to the next level, okay? JStack is probably one, if not the most important tool for production debugging. It's essentially the ability to come in and look at what a JVM is doing. Okay, coming and taking a snapshot and seeing, oh, this is what the threads are doing. Okay, it's so foundational. Everybody knows it. But I love this tool, but there's a problem. There are two key problems with this piece of technology, which render it a lot of the time useless for the kind of problem issues that we have to deal with in production. And I want to talk to you about a technique called preemptive JStacking, which essentially helps solve these issues. The goal here is essentially to have the system auto-diagnose itself. That means nowadays, if a server is hanging, we're seeing a production, say you're running one of your nodes is slow. Okay, in your Spark cluster, your Akka, something CPU is high, throughput is low. Okay, that node is hanging. Okay, gets taken off the cluster, gets recycled, the JVM gets restarted. you as the developers are kind of in a problem because you don't really know what happened there. Okay? You have to come in, you have to try and instrument the code. It's very hard to know. What you ideally want to do is be there when that JVM is hanging or is essentially meeting that threshold and be able to say, give me a JStack, one that's stateful. I want to see what it's doing and what it was doing at that moment. The thing is with JStack, it's a command line utility. You're not there to activate it. What you want to do, and this is a little sample that I put up on GitHub, essentially, is you want to have the code, actually the application, self-JStack itself. Meaning, we want to have a thread. This is a utility we've built into our production environment. I've talking to many very sophisticated companies within our domain. They do that as well. Essentially, they have threads which are polling the internal system, looking for a specific case. For example, looking for a specific decrease in throughput. In which case, the system, what it will do, it will launch a JStack against itself. It just emit that to file. Or you've seen more sophisticated company even emit that directly into their log stash. So they can come in and see whenever a server is hanging, okay, they can just come into their logs, pull directly from the log stash. Even the machine has been recycled. They can come in and see a JStack at that point in time. Okay? This is a very powerful technique. And of course, if you've added state information into the thread name, that JStack has now really been amped up because you'll be able to see exactly what part of the stream it was doing, what job was it processing. So you see those techniques will play well together, okay? Using modern logging combined with preemptive JStacking, combined with thread state naming. And some triggers that you might use to take a self-JStack can be queuing exceeding capacity, throughput exceeding. My favorite one, by the way, is deadlocking. Okay? This is a cool trigger. If the JVM deadlocks at any point in time, okay, and I want to know, deadlocks are the worst. They're sporadic, they don't happen, they're hard to reproduce, they have a tendency to happen in production to usually our most valuable customers. This is a cool trigger. I can come here and when the JVM auto-detects through the JMX runtime beam, there's a deadlock, take a JStack, okay? Log it, send it to Logstash, let me know about it, okay? Complete with what the JVM was doing at that time and dynamic state information for that, okay? Again, pretty cool. There's a bunch. All this code is on GitHub. I'm just throwing you guys ideas that we found have helped ourselves and our customers kind of get themselves out of very hairy situations very quickly. Want to move over to the next tool. I'm kind of running you through a bunch of stuff here, okay? Taking up a level again, which is B tracing, okay? This is an open source utility. Not a lot of people know it, unfortunately, but I found myself to be one of its stronger proponents, and a lot of our customers are now using it. This is an advanced open source kit which essentially enables you to interrogate any live JVM for almost any bit of state which you're interested in without restarting the JVM, changing the code, or modifying its state, which ops people love. Because this tool guarantees that you will not actually be modifying the state of the JVM, okay? This is a pretty cool tool. The only con to this tool, which I'll also touch on some techniques to mitigate, is that because it is read-only, it limits you in your ability to do stuff with it. And we'll touch on that and show you a couple examples super quickly, okay? Again, you don't have to restart your JVM. You can even attach remotely to a live JVM production. You don't need to be on that machine, okay? You can attach it to JVM. It's super easy. You can either do that through an API, the Virtual Machine Attach API, or, and by the way, you can see exactly how to use this bit here. It's super simple. All you do is just do btrace. You target the JVM you're interested in. You give it some commands, which I'll show you in a second. It can start doing some really wonderful things. In terms of restrictions, here's the con. Because the tool does not allow you, by design, to change state, okay, there's a ton of things you cannot do. You can't create new objects, okay, and you can't log stuff. You can't even loop, because hot looping, okay? But you can still do amazing things with this tool. I'll show you if you want to do something that you can't do here. We'll touch on some techniques to do that, okay? But let's get to it. Okay, this is a sample btrace script. Essentially, it's written in a Java-like syntax, which essentially enables you to write meta scripts, which will run on top of your code, okay? This is very powerful. This little script here, okay, tells the JVM, hey, whenever somebody in the JVM is writing to a specific file, give me a callback, okay? A lot of the times you're trying to debug a lot of strange I/O activity on this node. You're trying to figure out why is it working so hard? Where is it coming from in the code? You don't know, okay? What are some of the situations? You want to monitor this, okay? Take this B script, okay? Everything, these are live samples you can take from the site, okay? And you can just tell it, you know what? This resume here, you know, whenever somebody creates inits, and it's just the JVM word for constructor, okay? A file input stream for each one of those, okay? Just let me know about it, okay? And of course, you can put in, no, if somebody's writing more than X amount of information to the file, to a specific folder, okay? Give me a JStack, okay? Print this, send the information, store the information, okay? So you can do a lot of amazing things with this kind of tool. You can do this for actors, okay? Whenever somebody's calling into this actor under these circumstances, okay? I want to know about this. But the beautiful thing about this is you can, with btrace, you're not limited to just instrumenting your own code. You can instrument any class within the JVM, a file input stream, a a database connection pool, a thread pool, and really go deep with this. Again, this tool merits like a whole day tutorial. I want to let you know, guys, this option is available here. Take another cool example, which I really love. A class loader hill, okay? Now, classes are being loaded, okay, or reloaded into your JVM. You're not really sure who's loading them or why, okay? Especially if you have like some system which like compiles stuff dynamically for templates. You're getting a lot of recomposer stuff, you know, because if like you play something, you know, a lot of dynamic compilation trying to figure out, you're no longer just, here's the class path, okay? It's more like, you know, there's a lot of dynamic stuff going on. Whenever somebody loads a new class, I want to know who's doing it and why. They already have within the btrace utils thread.jstack. Okay, give me a snapshot of the entire JVM when that class was loaded. Okay, needless to say that of course if you've enriched the thread state previously, the JStack which you're going to see here will be much more informative. Okay. Another cool example for profiling stuff, okay? Can I get a callback anytime somebody within the application initializes a buffer, a byte array, or a character array? That would be pretty cool, okay? I want to counter that. I want to profile that under specific condition. Can I do that? You can, okay? You can come in whenever somebody instantiates a new character array, okay, anywhere within the application. Look at the regex. Super important. You know, whenever somebody initializes that, or only within a specific package, okay, or in a specific class, give me a callback. I'd like to know about it, okay, because something's fishy and this could help me, okay? So again, I can go on. This tool is very, very powerful. I really encourage you to take some time to learn it. It might help you down the road. I know it helped me. Let's take it to the next level, talking about Java agents. How does btrace work? It's not a JDK tool, so it's not something that's using any like secretive like JVM level stuff. It's not something that's made by Oracle or part of JDK. It's built upon one of the most powerful JVM technologies, which are Java agents. Okay, which essentially power most of the modern performance management, profilers, debuggers that we use in production today are powered by this technology, okay? Which essentially enables people to, folks like the people who wrote btrace, like us, okay, to really do some amazing things within the JVM. Now, there are two types of Java agents, very different ones within the JVM. The first one are called Java agents. They're written in Java. They're fairly easy to write. Okay, they operate as almost normal JVM code, and that's how btrace is written as a Java agent. Because Java agents essentially what makes them so special. Why am I being so hyped? Why am I hyping this technology? Because Java agents are essentially components on the code to which the JVM gives special permissions, such as modifying code at runtime, which is what btrace is doing essentially. You're giving it commands to go into live classes which are running in memory and change their code. But because this is, with great power comes great responsibility, that's also why Btrace, the designer of Btrace, have implemented all these limitations. Because just doing anything within the JVM is usually can be risky, especially in production. That's why I love Btrace so much. So you have Java agents, which are written in Java. I'll show you an example of one of those in a minute, okay, and some of the cool stuff that you can do with that. That's the first one. The second one are called native agents, okay? And those are a whole different beast and are very, very interesting. So just to sum up this bit, okay, the pros are that these tools are extremely powerful. They give you different levels of control on which we'll touch. There's a con, though. Okay, other than the great power responsibility a bit, the second issue is that the JVM is polyglot and is fairly language agnostic, which means even if we're writing Java or Scala Z or whatever language that we're using to code, when it comes down to JVM, it only knows bytecode. Okay, kind of that's the language which parses the JVM. So for you to interact and write your own Java agent, you need to learn how to work with bytecode. Good news is there's a bunch of really cool tools that help you learn really quickly and really get you up and going super quickly. Okay, so as I said, two kinds of agents. The Java agents are by their name are written in Java. Okay, I'll show an example in just a minute. The second one are the native agents. As I said, they're a completely different beast. They're written in C++. They're native. They access the lowest levels of API provided by the bytecode specification to any developer called the JVM TI, the tooling interface. This API is extremely powerful. You can do stuff there that you could not dream of doing when you're writing straight up Java code. You can get access to the JIT compiler. You can get callbacks whenever garbage collection happens with insights that you would not be able to obtain using straight up Java code, okay? Locking, synchronization. You can tell, whenever somebody locks this object, give me a callback. The JVM will direct a C++ call to you. Whenever an exception gets thrown, okay, I want to know about it anywhere within the application and where it's going to get caught, okay? So powerful tools are available here. The APIs themselves are not very easy to consume. They're kind of cumbersome. But if you get hold of them, they're very powerful. Okay? So that is kind of the pro side. A few cons. Platform dependent. This is C++. So if you want this to compile on your favorite Linux distribution, you're going to have to make it happen. Second bit is you really have to know what you're doing because some of the hooks or some of the capabilities can have performance impact on the JVM. Okay, some hooks change how the JVM JIT compiles things, and you run the risk of de-optimizing code. Okay, so that's the one thing. And the third bit, which is probably the most important one to know, you are no longer in Kansas, meaning you are no longer protected by the JVM. If you have an exception within a native agent, okay, this will not be caught by the JVM and translated from a dangerous SIG-SIG into a null pointer exception. This is a SIG-SIG, okay, and if you don't deal with it, you can potentially crash the JVM, okay. So with great power comes great responsibility. Again, I encourage everybody to kind of learn more about this technology. It just gives you a deeper understanding as to how the JVM really, really works. And but with that, let's take an example, okay? I want to show you an example of an actual Java agent, okay? Because I think 90% of the time, that's if you're ever interested in doing one of these or you need one of these, that's probably what you're going to end up doing. Again, all samples are up on GitHub. Essentially, what you have to do is very simple. To run your Java agent, you can either just compile your jar file, okay? There's something you need to add into the manifest, okay? This little thing it's up on the GitHub as well. You can see that there. Super easy to do. You either add this argument to your JVM or you can attach an agent to a live JVM, which is what Btrace does. It uses this capability to essentially attach a Btrace agent to your JVM to let you write something that will modify code in a safe way. But let's say, for example, you want to log something. Let's say you have this really, really hard performance problem, and you want to make sure that under specific situation, which somebody's allocating objects of a specific sort, or a specific threshold within the thread pool exceeds, you want to log, okay? Because this, you want to have that information be sent over through Logstash into your dashboard or be alerted about it. You can't do that with btrace because logging mutates the state of the application from the JVM's perspective. You are writing to disk. You're instantiating object. You're doing a stuff which is dangerous. So btrace won't allow you to do that. But with this little thing here, you can do that. All you have to do, you write a pre-main. This jar file, instead of a main method, which is what a standard Java application, or with Scala is going to be different, the entry point into your code, you are writing a pre-main method. This is a name which the JVM identifies. It will look for a pre-main method. The reason being, it's going to give you the keys to the castle. It's going to give you an instance to this object here, the instrumentation object. Only available to Java agents. You cannot get hold to reference to this object from normal Java code. The security machine with the security mechanism will not allow it. The only way to obtain this is only if you have physical access to the JVM by either attaching a startup argument or you meet the security requirements for the virtual attach. If you do get an instrumentation object, you can attach a transformer, okay? Transformer within this context, okay, means an object which all it has to do is just implement this interface here. Bytecode in, bytecode out, okay? Whenever the JVM loads a new class, doesn't matter if it's come from a jar file, a WAR file, from play, or the bytecode was generated by whatever mechanism. It's going to go through this sync from the JVM's perspective, and it's going to run through your transformer. You can even be a bit cheekier and ask the JVM to run it through your hook for a class that's already being loaded, which again is what btrace does. It takes your classes and attaches itself to them. In which case, it will give you a callback to this transform method that's over here. And at that point, you need to essentially provide bytecode. Remember that little con I told you about? You have to be able to know bytecode. This is where it kicks in. Okay. Luckily enough, there's amazing tools out there to get this up to speed. So, for example, if you want to instrument a method, my favorite tool. There's a bunch. There's Aspect, J, and Weavers and stuff. I love ASM. It is a great library. It's well documented. It's super robust. And it's super easy to use, and has a great Eclipse plugin, which I'm going to, and an IntelliJ plugin as well, which I'm going to show you in a second, which makes life so much easier. Okay, so all you have to do when you transform, you read the class into a reader. You're going to have the target transformation is going to go through a writer, pass that on to him. Okay, through a visitor method. They use heavily the visitor design pattern, way which you visit the bytecode that's coming in. Okay. All you have to do here essentially is come in and say, well, you know what? I want to instrument the constructor. If this is not a constructor, skip. But if it is the constructor for this specific class, which I want to monitor, again, this can be a character array. This can be, something in a thread pool. Okay? Pass this on to this little class here, the method visitor. This is a class which will enable you to manipulate a method, a bytecode method that's being loaded into the JVM. Okay? Visit the code, and then use ASM to add a new method into the code that's being loaded into the JVM, which is going to get compiled to call into my code, which is essentially this. This is my class. This is my hook. Okay? And what I want to do here is call my code, okay, or log something, or run some logic which I want to perform. In this case, if something is interesting to me, and some threshold has been exceeded, or a deadlock, or whatever it is I'm looking for, okay? Hold on. Activate a JStack, for example, okay? Or log something. At this point, I can essentially do what I want. So this enables you essentially to do everything that btrace does. Instrument, a thread pool, a database connection pool, Akka, play, Spark, your code, your friend's code, and essentially be able to instrument and add your code to it. This is how most of the modern tools that we use every day, commercial solutions, that's what they do. Now, the last thing I kind of want to show you, okay, because I do see we're kind of running out of time. I have more stuff and more surprise, but unfortunately won't be able to get to those today, is the ASM bytecode plugin. This is an extremely important piece of code, okay? I'll show you what it does super quick. This is my Scala IDE. I've just switched to it. I've just opened up a small sample here because if there's a lot of bytecodes. If I want to show like a big one, we'll get lost in it. But this is super cool. This little actor here, what it does, you just stand on a method. It'll actually show you the bytecode or the code, the ASM code you need to write to generate that code. Okay, so you switch between two modes. So you can come in, well, this is what I want to instrument. You write the code in Java or in Scala, okay? And this beautiful friend here is going to show you both how the bytecode looks, but also how to generate it. What you need to put into your agent, essentially, to inject that code into the JVM. So, and this is, by the way, I think, just having the ability to read this and understand this, it's been incredibly helpful to me, like even understanding like how Scala works, how the compiler works. This is like my actor receive method. So I can go here, I see, hey, what are they doing? Creating a new anonymous function receiver to object, duplicating it, loading this, and then calling its constructor. So essentially, this is a function which returns an object of this kind. Cool. Let's see what this object does. Okay, jump into here, apply or else. This is the method which actually produces what I want to instrument, for example, the actor receiving a specific form message. And I can see it doing some stuff, checking that, and I know Roland is doing actually a talk, this event, about typed message dispatching between actors, okay? So this is here, actually, the Scala compiler checking that the message that is being passed, the object that's being passed to here, is actually of the correct type. So this is pretty cool. You really understand what these guys are doing, and then, of course, you can come in and instrument that. And then you can see actually how it does the print line. So you can come in, look for this code with your Java engine, even with btrace, and do a bunch of really cool stuff here to essentially enable you, at the end of the day, get to state that otherwise today with standard debugging or logging tools, when you're trying to solve an issue in production, is unavailable to you. Okay, so just wanted to kind of touch a bit of this, and even like the tools that we build as a company. This is like for extracting state and code. It all goes to this. Okay, if you see like the code, like an exception in runtime, and being able to see the state for an exception, for an error, it is all built on JVM TI and Java agents. So this is, and essentially, all commercial vendors use these technologies. So I just wanted to kind of tee that up. Interesting, by the way, is that one of the things that we are doing as a company, and this is also one of the reasons why I'm here, we're subbing, is we've actually been working on a research project with Typesafe about adding some very interesting instrumentation bits to make Akka more debuggable and more visible to folks who use it at high scale. So this is an early research project that we're working on, and if some of you guys are working with Akka and would like to come and kind of share your experiences with either us or the good folks over on the Typesafe booth, the engineers there, would love to talk to you and actually learn about some of the challenges that you've had in debugging production code for Akka, because that is something that both companies are very actively looking to solve, and we're reaching out to the community to provide us with feedback on that. I think my time is up. With that, all I have to do is thank you for your time and wish you a happy and productive Scala Days conference. If folks have any, I think if folks have any questions, we have till 2 or 2:05, by the way. 5 minutes. We have 5 minutes for questions. If people have any questions on this, on Java agents, on instrumentation, and JVM TI, or something, happy to answer those. Please. So creating a stack trace is something that you do when the chips are down. I mean, you don't do it. I wouldn't do it like every second. It's not incredibly expensive, but I would not say this is like incrementing a counter. You usually want to do that, I would say, in spans of like a minute or something, or like 30 seconds. You can take a StackTrace, you can take a JStack, but it's not a real-time operation. Changing thread names, by the way, is a real-time operation. There is almost no cost to changing, to continuously mutating and updating thread naming. So when you do take the JStack externally from another thread, you don't take a performance hit. If you go look at the implementation for setting thread names, it's simply setting a string member. Okay? And to obtain the current thread is also a real-time operation because the pointer to the current thread is a register on the actual native JVM stack. So changing thread names, real-time, taking JStacks, I would say about every 60 seconds, please. So what I would usually do is I would usually encourage you to use that in a try finally clause. Now, a lot of the times, one of the things that we do, and I've done this many a time, is I, in my code, just do the simple thread name without a trycatch, without any of that, okay? And I've written a Java agent, which then later comes in and changes the code, okay, to do a trycatch and restore the thread name before it goes back to the thread pool. So when I'm coding, or we're coding internally, we just change the thread names. We don't think about it. Then we know later on, when the JVM runs, okay, we've written a little Java agent which does a simple try finally and resets that state for us. But that is a good question because you want to make sure you don't completely, especially the worst case scenario, if like somebody's changed the thread name, somebody didn't reset it, it goes to another thread who's doing something completely different, but doesn't have essentially that bit of code implemented. That's bad. So that's what we do the Java agent for. Well, the different machines goes back to what I said with foundation logging. That's a distributed transaction ID. That's why you want to make sure, okay, that thing we talked about in the beginning, which you assign to any entry point in your application, you want to make sure that's persistent, especially with reactive applications where you're doing so much context switching between different threads and different JVMs. So that little boring piece, that's the only way nowadays to do that. But if you do that, and you have the thread names and the JStacks, and you connect that to Logstash, you can create really, really interesting infrastructure for production debugging and really, empower you in that respect. Sir, over there in the end.
With this changing the thread name, I think this also make it possible that you just log the context once in conjunction with the thread ID, and then you can sort it out later. And I kind of prefer not to be too intrusive with my code, but just log it and then use like a cross script or a Scala program or whatever to sort it out after every piece of information is there.
True. The only caveat I would add to that is that if you're using your MDC logging, for example, and you're really enriching that with context, when you take native JDK tools, such as JStacks, for example, they're not aware of it. They will not capture that. So that is why I said thread name is the only way that you can inject information into your stack traces. That is really the main reason why we do that. Other than that, definitely go with your MDC. Please. Use what? Yes, you can use multiple. The JVM it's been very intelligently designed to chain agents. So other times, if you guys have been running on a performance management and a profiler tool and a debugger together in some conjunctions, this is only because the JVM is able to chain transformations. So the first agent will either pass or take on a transformation. That information, the bytecode will then flow onto the next agent and over to the next agent, with the final result being loaded into the JVM verifier. One little note about, by the way, bytecode loading. The JVM is a very powerful bytecode verifier, which means if you load bytecode that's corrupt, incorrect, cannot be compiled, or is logically incorrect, it'll get rejected. Meaning you cannot load. The JVM is a safe machine. If your bytecode doesn't compile, is not valid, there's something wrong with it, it's not logical, you made a mistake, no worries. You're just going to get an exception back saying, and a lot of time that exception will actually tell you what's wrong with the bytecode which you've loaded. Okay, so that also happens a lot of time when you may be chaining two agents which do not work well with each other. But anyways, please, sir.
Have you not considered technologies like Aspect J, for instance? Because a lot of stuff you do tend to also do maybe not as low level as you would like.
Yes, so Aspect J, for example, and we're talking about static weaving, in which you change the build process. So if you're changing the build process, it's good, but it's a lot of times it's something that you have to do. It's forward tracing. You have to know that you have to come in and do it and change the application to give you the information. So if you can forward trace in that respect, meaning you know this information you need, then weaving has pros and cons to it. Essentially, you don't have to use agent technology, but on the other hand, you have to change the build process, okay? This is an internal decision. The primary benefit to these set of technologies is that you can come in and to attach to an existing JVM and capture state information without actually going and rebuilding the pipeline, redeploying and restarting the application, which in some scenarios can be hard. That's a Java agent. Yeah, so the ASM Bit is just my personal favorite technology because I found it to be very, very light, very dependable, and has a very powerful plugin. And this is my preferred technology of choice. Aspect J, by no means infer that I have that it's not an amazing piece of technology. I usually use Aspect J more when I'm doing like static weaving and stuff. That's been my experience. ASM is very light. You can include it within your application. It's just it's not even a jar file, it's extremely small. I like it. Aspect J can totally rock in that respect, using in conjunction with Java agents. Please. Yeah, that is exactly the research project that both companies are working on, and we'd love to kind of exactly come in and see what are the things that are interesting to you. So just reach out to the folks over at the Typesafe booth, or just shoot me an email. Okay, would love to hear some of your challenges. It is already 2:08. If somebody has like a yes/no question, I'll take it. Otherwise, I'll give you back your afternoon. Sir? That's not a yes/no question. I'll answer that. I'll do that offline. Guys, again, thank you so much for your time.